So we have question 6 now, and we're dealing with some collisions. A red puck of mass 2.0 times 10 to the minus 3 kilograms is set moving along a long frictionless track towards a blue puck of mass 4.0 times 10 to the minus 3 kilograms. That's twice as much as the red puck. The red puck has a velocity of 21 meters per second, while the blue puck is at rest but is free to move. Both pucks carry a positive charge of 1.5 times 10 to the minus 6 coulombs. The pucks meet along the line of their centre of mass in an elastic collision or interaction. The charges cause an electrostatic force between the two pucks. Okay, that's a given since they're both positively charged. When they're separated by distance r, the repulsive force is given by here, and this is the same as the gravitation formula, except in this case we've got charges instead of the masses, and we've got k as the constant instead of the universal gravitation constant. The electric potential energy is given by EP equals k q1 q2 over r, which as you may notice is there's no r squared, which is the only difference in this. That's because the electric potential energy is equal to the work done to separate the charges to a particular distance. That distance is the same as the radius. So it's force times distance for the work, which is this force here times the distance, which is r, which means one of the r's cancel and you end up with this. So it's just something interesting. Q1 and Q2 are the two charges, and k is constant given to us. That's nice. Okay, so summarising this in my mind, I will say it's like an air track. Two air hockey pucks, one twice as heavy as the other, or twice the mass, and they're both charged, and they'll interact according to those charges and according to the motion of one towards the other. Now, A says describe without calculations the motion of each puck as it interacts with the other. There's a couple of things to remember. We've got to deal with the charged aspect, so maybe we should deal with that first, but there's also the kind of a momentum transfer, so the charged aspect, as the red puck comes closer, there'll be a point where the force becomes meaningful, and anywhere beyond that, the radius between them, that's the radius, just in case you're having issues with that, but there'll be a point where beyond which it doesn't matter about the force. So the force will be kind of negligible when the red puck's closer, and then inside it'll matter. And you can see that because of this r squared factor, it'll make a big difference the closer you get, and the closer you get, the even bigger the distance according to that inverse squared factor. So as it decreases under a meter, and as it gets vanishingly small, that force is going to go huge. Okay, anyway, so that force is going to decrease the momentum, or be used to negatively accelerate the red puck, and that same force is equal and opposite on the blue puck. Since it's twice the mass, it's going to accelerate at half the rate that the red puck decelerates. Okay, that's just something interesting. It says without calculations, so I don't know if we need to get into that level of detail, but it's good to consider since we're dealing with F equals ma. That's an important one, and momentum is mass times velocity. These are all important equations. You can use the equations if you're talking strategy. Use the equations and consider what happens before and after for each puck. So before and after for each puck. So that's strategy. Okay, and another important thing to note is because the red puck is smaller than the blue puck, that means it's going to bounce off it, so it'll end up coming back. There's three situations you can have. One is when both the pucks are the same, in which case it's like Newton's cradle when you drop one of the things and it hits the other and then it stays stationary, and then the other one carries on. So that's when they're the same mass. when if the red puck was larger, then it would crash into the blue puck and they would both continue on in that direction to the right. But since it's smaller, it's going to transfer some momentum and it'll bounce back while the blue puck carries on. Okay, so that's quite important too. And another really important thing when you're dealing with the momentum, if you're considering the momentum of the center of mass, it'll be constant. I mean, the same amount of momentum is always conserved, so initial momentum equals final momentum, and so the momentum of the center of mass will continue along at the same velocity. The center of mass of the system will continue at the same. Okay, so I think that covers more than enough for that. They'll be after relatively concise explanations about the charge leading to electrostatic force, which would decrease the speed of the red puck and increase the speed of the blue puck. And as that separation increases, again the force would decrease. Yeah, total momentum is the same. Yeah, mostly velocity, because it's talking about motion. It's mostly concerned with the velocities of the pucks. So you can go through all of that and draw out the information. Okay, B. At the instant of closest approach, both pucks are at the same velocity. Okay, explain why this is so and show that the velocity is 7.0 meters per second. I think it's probably easier to show it than to explain it, but your initial momentum has to equal your final momentum, and your initial momentum is just the mass of the one puck, which is 21. The momentum of the one puck, which is 21 times 2 grams, 0.002, which is 2 times 10 to the minus 3 kilograms. That has to equal, since we're going at the same velocity, it'll be the sum of the masses, which is 0.002 plus 0.004, times by the shared velocity of 7 meters per second. Oh wait, you don't know that, you're trying to find it out, V, because it's a show question. Always use the answer given to you just to check it, not to find out, or because yeah, it's back to front. Anyway, so you've got an equation with one unknown. If you multiply this out and rearrange it, you'll see that V equals 7.0, because you should stick with your significant figures. I think they gave you those to all to 2, but you can double check that up there. So that's the easy part. Understanding why at the closest approach they both have the same velocity. Well, there's got to be a point as one puck's getting closer to the other where it won't. The forces will be it won't be able to come closer. They won't touch because of that electrostatic force that is exponentially increasing as the distance reduces to nothing. So they won't quite touch, and there's got to be a point as you're accelerating the one to the right and you're decelerating the one to the left, where they both I don't know, you can think of it at the point where this one decreases enough and then turns around and goes back in the other direction, and the other one is accelerating from nothing. So one's going from 0 up, one's going from it's 21, isn't it? 21 down, and it hits 0 at some point and then increases. So they both have to pass through the same velocity at some point, and the closest approach is the point where it starts. This is a good point. Where well, the force is at its maximum. So that means it's not going to get any closer because it's going to start decreasing in that force, and that means, I guess, it's going to start accelerating the other puck. Well, it was already accelerating in the opposite direction, but it's going to be accelerating at a lower rate. How's that? Because the force is going to be less. But in any case, it can't be getting closer to the puck after that point. How's that? A little bit vague, but the marking schedule doesn't give a lot of detail either, so I think I've covered that more than enough. Okay, they talk about relative velocity. The pucks, when they're at their closest point compared to the air track underneath, will be travelling at the same speed, which is both together in that direction, and at 7 meters per second. That's not to say that the speeds are still going to aren't going to keep changing, because they will. This puck will accelerate more, and this puck ends up going back in the other direction. But as they, yeah, no, I've explained that to death. That's good enough.